All right, if you're a physics student, you've definitely heard the name Irodov. His problem book is kind of legendary. It's this boot camp of brilliant and, let's be honest, seriously tough physics problems. Today, we're going to roll up our sleeves and tackle one of the classics, Problem 1.106.
You know that feeling, right? You're staring at the page, you've got forces going in all sorts of crazy directions, and the actual path to the answer just feels like it's completely hidden. It can be super frustrating, but here's the thing. These problems are basically just really clever puzzles. And just like any good puzzle, there's always one piece, one little hidden clue that once you spot it, everything else just clicks into place. So for this one, we're going to become detectives and find that clue.
Okay, let's get into it. Problem 1.106. The setup is this. We've got a disk on a ramp. We give it a shove, so it starts moving sideways, purely horizontally. Our job is to figure out how its speed changes as gravity and friction start pulling it down and making it turn.
So let's paint a picture here. You've got a ramp tilted at an angle alpha. You place a disk on it and give it an initial push V0 straight across the slope. The disk starts to slide and turn downwards. What we want is a formula for its speed, v, at any point where its path is turned by some angle phi. And look at that last piece of info. The friction coefficient k is exactly equal to tan alpha. That doesn't seem random, does it? That's our clue.
All right, step one. You know the drill with any dynamics problem. First things first, you have to draw your free body diagram. We need to get a handle on every single force that's pushing or pulling on this disk.
First up, the old classic, gravity. Good old mg, pulling straight down toward the center of the Earth. Simple enough. But because we're on a ramp, we know we're going to have to break it down into components pretty soon. Now, obviously, the disk isn't falling through the ramp. And why is that? It's because the ramp is pushing back. That's the normal force, N. And the number one rule for the normal force is that it is always perpendicular to the surface. And finally, the force that makes things interesting, friction. Now, this is kinetic friction because the disk is moving. And here's the rule you absolutely have to remember. It always points in the exact opposite direction of the velocity. So as our disk turns and its path curves, the direction of that friction force is going to turn right along with it. Okay, this is where we put on our detective hats. The people who write these problems, they love to hide the key to the whole thing in plain sight. And in our case, the big flashing sign is that weirdly specific value for the friction coefficient. Right there in the problem statement, it tells us that k equals tan toph alpha. Now you've got to ask yourself, why that value? It's not a coincidence, it's not random. The author basically just handed us the key that's going to unlock this entire problem. So let's unpack that. What does this clue actually do for us? We know the friction force is just k times the normal force, n. We also know the normal force is just balancing out the component of gravity that's pushing into the ramp, which is mg cos alpha. So now let's plug in our big clue. We replace k with tan alpha. And what's the definition of tangent? It's sine over cosine. So you get sine alpha over cosine alpha times mg cos alpha. And look at that. The cosines just cancel right out. It's beautiful.
And boom, there it is, the aha moment. The force of friction has the exact same magnitude as the component of gravity that's trying to pull the disk down the ramp. They are perfectly matched in strength. This one little fact changes everything.
Okay, so we've got our forces, and we've uncovered this incredible secret that two of them have the same magnitude. Now let's add them all up as vectors and see what the real total net force on this disk looks like. Okay, so let's think about the net force that's actually along the plane. We've got two main players. First, that gravity component pulling straight down the slope, mg sine alpha. That force is a constant vector. It never changes direction. Then we've got friction, which we just found has the exact same strength, but its direction is always changing, right? It's always fighting the velocity. So you're adding a constant vector to a rotating vector. And what does that mean? It means the total net force is constantly changing. This is a super important point, and it's a classic trap in these kinds of problems. Because that net force is changing, the acceleration is not constant. You cannot just go and plug this into your simple kinematic equations like v equals v0 plus at. That's not going to work. We need a much smarter way to attack this. So if the easy formulas are out, what do we do? Well, if you can't solve a problem from one point of view, you change your point of view. Instead of a fixed x and y axis, we're going to use a special coordinate system that basically rides along with the disk.
We're going to split the acceleration into two useful parts: a tangential part that's along the direction of motion, and a normal part that's perpendicular to the direction of motion. The car analogy is perfect here. The tangential acceleration, AT, that's your gas pedal on your brake. It's the thing that changes your speed. The normal acceleration, AN, that's your steering wheel. It's what makes you turn. To solve this whole problem, we just need to figure out the equations for the gas pedal and the steering wheel. So you do a little bit of trigonometry, you break your forces down along these new moving axes, and you end up with these two equations. The top one tells you how the speed v is changing over time. The bottom one tells you how the turning angle phi is changing over time. Now you see that dt term in both of them? That change in time? That usually spells trouble. It often means you're about to do some really messy calculus. But watch this. This is the really clever move right here. What happens if we just divide the first equation by the second one? The dt terms on both sides just cancel each other out. And what we're left with is this amazing, simple equation that directly connects the change in speed, dv, to the change in angle, d phi. Time is just gone. We've completely kicked it out of the problem. And from here, it's pretty much a straight shot to the finish line. All that's left is to integrate this much friendlier equation. You integrate the v side from your initial velocity to your final velocity, and the phi side from your starting angle to your final angle. You solve the integral, clean it up, and you arrive at this. Just an incredibly elegant final answer. It tells you the exact speed of the disk based only on how much its path has turned. So we got the answer. But what's the real lesson here? It's not about memorizing this one formula for this one problem. It's about the strategy, the playbook you can use the next time you get stuck on a problem that seems impossible. So let's run through that game plan one more time. 1. Always start by mapping out your forces. 2. Be a detective. Hunt for those special conditions, those little clues the problem gives you. They are never random. And 3, this is the big one, if you find that your net force and acceleration are not constant, don't panic. Just change your perspective. Think in terms of tangential and normal components. It's a powerful trick that can make a really messy problem suddenly become simple. And I'll leave you with a final little puzzle to think about. Our answer, it's more than just a formula. It describes a very specific mathematical relationship between the disk's speed and its direction. And that means the disk traces out a very specific, predictable shape on that ramp as it moves. Any guesses what that shape might be? That's a great one to chew on for next time.